Okay, so this is the lecture to replace the one on Thursday. Where we left off was we were talking about special matrices. We had talked about matrices of the form we see here at the top of the page, where you have A transpose times itself, and what that gives us is a square, and if the matrix is of rank P, where P is less than n, it gives us a square positive definite matrix. So one of the other matrices that we talked about being special was a positive definite matrix. And one way to think about this is kind of the analog of squaring a number. So then the positive definite matrix is the matrix analog of a number that is squared, or really just a positive number, because any positive number you can take the square root of. Okay. We also talked about orthogonal matrices. We said that they were matrices whose transpose was also its inverse, but geometrically we can understand a orthogonal matrix as a rotational operator, so it's distance preserving. All right, so I want to pick up down here, continuing to talk about positive definite matrices, and they're going to be useful for describing something that I'm going to call statistical distance. Okay, so what the notes begin by doing is they start by reminding us of our usual notion of distance. We may be used to thinking of distance between two vectors x and y of being the square root of x1 minus y1 squared plus ... plus xp minus yp squared. Well, that's exactly what we have written here as x minus y transpose x minus y, and then of course square rooted. The notes also talk about the distance between x and 0, and this is what we think of as the norm of x. And of course that is just x transpose x to the 1/2, square rooted again. Okay, so the notes just go on to say a little bit more about distance. There's nothing, going back to what we had earlier, this is usual Euclidean distance, as you're familiar with it. But there's nothing that says we have to measure distance that way. And there are some general rules for distances, or this is the mathematical notion of metric. We have a valid metric if we take the any two vectors in our vector space and apply this function to them, this distance function to them, if it always returns a number greater than or equal to 0, and if that function, when we plug in two vectors x and y, returns 0 if and only if x equals y, then this is a valid distance or a valid metric. So what we're going to do is we're going to think about a different type of distance down below. Okay, so the notes set this up by saying, notice that our notion of distance, which we had on the previous page of x minus y transpose times x minus y to the 1/2, that is equal to this expression here, where we throw the identity matrix in. And what we're going to do is we're going to replace that identity matrix with a positive definite matrix. Okay, so let's put some pictures to these ideas. What we are used to doing is taking the distance from two vectors. In the previous notes, or in the previous pages, they were x and y. I have these written as x1 and x2, but keep in mind that x1 is in fact an ordered pair. It would be x11, x12 here in two-dimensional Euclidean space. That underline is reminding me that it's a vector. The difference is just I've got this 1 and 2 subscript to remind me that these are different vectors, right? Of course, the Euclidean distance is given by the length of that piece of the triangle that I've drawn there, and so if we computed the Euclidean distance as the way we normally do, we would get the same thing as if we were to put a ruler on that segment that I've drawn. Of course, that is obtained from the Pythagorean theorem. And then another way of thinking of that is this would be equal to, well, we also talked about the distance of between x and 0, which is giving the magnitude of the vector. So that's, in this picture, we have some pictures of what that should look like. And here's the distance of x1, here's the distance of x2. Now, we can actually think of the distance between two vectors in this way, because we can just take the distance of x1 minus x2 and 0, and that in some sense shifts this picture here, this first picture. It would take the difference between those two, and we would see that we'd get if I take x1 minus x2, the first coordinate of x1 is larger than the first coordinate of x2, so that would shift it to the right. If I take x1 minus x2, the second coordinate of x1 is smaller than the second coordinate of x2, it would shift it down, and we'd end up with a vector down here, which would be x1 minus x2, and its distance from 0 would equal that segment of the triangle as before. Okay, so that's what I've tried to draw here. Okay, now let's change. So all we've talked about at this point is Euclidean distance. Let's think about why we might want to measure distance differently. Okay, so imagine I have a cloud of points, as I've shown down here, and this cloud of points is not symmetric. It doesn't, its contours would be ellipses and not circles. And let's think of two locations. So I have location 1 here on the vertical axis up here. I have location 2 shown in red on the horizontal axis. And if I were to say what is their distance from their Euclidean distance from 0, so just the magnitude of those vectors or those locations, you would come up with the same thing. The Euclidean distance of location 1 is equal to the Euclidean distance from location 2, those distances from 0, right? Okay, but that Euclidean distance doesn't take into account the cloud of points. So given that if we think of this cloud of points as data, let me pose the question a little bit differently. Which of the 2 points seems more unusual? So there, you're taking into account kind of but you're taking this, to answer that question, you might take this cloud of points and to kind of fit a density to it. And you might think, oh, location 1 appears to be more unusual than location 2, because location 1 is closer to the edge of this cloud of points than location 2, right? And so what we'd like to do is create a distance which accounts for that. Now, notice this cloud of points, although it's not circular, its ellipses are aligned in terms of the axes. So for this picture, it might make sense to do a variance adjusted distance. And this, we're going to ignore everything below this squiggly line for the time being. So now what we could do is we could take my notation here might not be ideal. Here I have a vector x without a subscript, so x has components x1, x2, x3 up through xp, and the distance from x to 0, we could adapt the distances to account for the variances in the individual directions. And so, for instance, in the previous picture, S11, of course, there would only be two dimensions, right? So we'd have S11 and S22, and then this would all be cut off here. S11 would be larger than S12 because the cloud of points was stretched further in the horizontal direction than in the vertical direction. And so when we plug in the points, the point along the vertical axis, we would get a smaller value than when we plug in the point for the horizontal axis. Now, we can actually compute this same thing. So this distance hopefully makes some sense. We're just accounting for the variance of the points that we're seeing. But another way to write that would be to put the variances on the diagonal. We'd have zeros elsewhere. And we can rewrite our distance in this way. We have x transpose times the distance times x. So you plug in any vector, whether that's the point on the horizontal axis or the vertical axis or any other point, not even on the axes, and you adjust the distance by throwing this d in here. And you can show that our rules for distance are preserved. So it's always going to return a positive number, and the only way we're going to get 0 out is if we essentially if we plug in the 0 vector, or if this is replaced by x minus y, if those two things are equal. Okay, so that's variance adjusted distance. We can take this one step further. Now let's consider a cloud of points that again is elliptical in its contours, but now it's not arranged in its the axes of those ellipses are not aligned with the axes of Euclidean space, of the horizontal axis and the vertical axis as I've drawn here. We could do the same game where we say, okay, let's consider two locations. And of course, I picked two locations that are equidistant from 0. And again, this location here, this location here would appear to be more unusual than this location here. The second one that I've circled, the one I just drew the arrow to, is in the direction of most of the points, whereas the first one, this one that I'm circling here, is less in the direction of the points. So this one would be more unusual, and it would have a greater distance. Well, how do we account for that? It's actually very easy. What we can do is we can put in the covariance matrix. Here I've got S because I've got this cloud of points, so I'm assuming I don't know the true covariance matrix sigma, but I can estimate it and place it in there. But regardless, it's a positive definite matrix. And we can define a distance this way, and it's going to meet our rules of distance because it's always going to return a positive number, because that's what it means to be positive definite, right? And so this is what we're going to term statistical distance. We can think of quantities like this as providing meaningful distance measures for data with covariances. And this is known as the Mahalanobis distance. Oftentimes in class, I will just refer to it as statistical distance, but this idea of statistical distance is going to come up in several of the procedures that we discuss in this class. Okay, so all this says is exactly what we just said, that if here in general. I mean, I motivated this new notion of distance by talking about data and its associated covariance matrix, but in general, you can, given any positive definite matrix, you can define a distance as we did, and it will be a valid metric. It'll be a valid distance. And this just says that this, if we have a positive definite matrix, this expression is known as a quadratic form. You can kind of think of it as a function of x. Depending on the vector x you give it, this is going to return a number. And so we can think of, well, that is described as a quadratic form, and it's very much required that A is a positive definite matrix. Okay, I'm going to stop the recording here just because it's easier to upload with a shorter recording, and then I will continue on with the lecture for Thursday in another video.